Here's a problem dealing with spring potential energy. The situation is this. We have a ramp, and there's a spring attached to the base of the ramp, and we place a 0.2 kilogram block against that spring and then compress the spring so the block is at the base of the ramp. Now the spring is pretty stiff, so it has what's known as a spring constant of 1400 newtons per meter. In other words, it takes 1400 newtons to compress the spring a distance of 1 meter. The distance the spring is compressed is 0.1 meter. We compress it. The angle is 60 degrees for the ramp. We compress the spring and then let the block loose. The block is then launched up the ramp a distance r. What we want to find is that distance r that it's launched upward along the ramp. And first of all, we want to try finding it assuming there is no friction, and then we'll try it a second time, this time assuming there is friction, where there's a coefficient of kinetic friction of 0.4. Well, first we need a little bit of background. We've never dealt with spring potential energy before, but it's not much of a difficulty. The potential energy of a spring, unlike that of the potential energy of gravity, it's 1/2 times the spring constant K times the amount of length that the spring is compressed. And in the international system, of course, we would use meters for our distance that the spring is compressed, and then that spring constant there is just what I gave you in the beginning. In this case, the stiffness of the spring is 1400 newtons per meter. I'd plug that right in here. Okay, and of course the units for potential energy of a spring are in joules. So that's the only new item that we have to deal with. One approach we could use is just using the formula for the law of conservation of energy. And let's just do it if no friction. So first of all, assuming no friction, we can just say that we'll just call this, when the block is compressed all the way to the base, we'll call this position 1. I'll do that in red. And then the position that it reaches would be position 2. So position 1, position 2. Alright. So assuming no friction, we can say that the potential energy of the spring at position 1 plus the potential energy due to gravity at position 1 plus the kinetic energy at position 1, we'll set that equal to the potential energy of the spring at position 2 plus the potential energy due to gravity, gravitational potential energy at position 2 plus the kinetic energy at position 2. And at position 2, the block is at rest. Okay, this is where V is equal to 0. So it just barely makes it up there. Doesn't have any speed up past that point. Okay, so we'll go ahead then and just start substituting in. We have the potential energy of the spring at position 1. That would be 1/2 kx1 squared. Now, since we squeeze this all the way down to the base, that block then would be at the baseline, so the gravitational potential energy would be 0. So imagine squeezing this block down so that it's right at that base where we define this base as having a potential energy of 0. The block is at rest at that point. It's motionless, so the kinetic energy then is also 0. So these two drop off. Potential energy of the spring when the block gets up here would be equal to 0. the gravitational potential energy of the block would be equal to, well, I'll just put that as m times g times h2, h2 being this height right here, and then the kinetic energy at position 2 would be 0 again. All right. So what do we have? If we plug our numbers in, we have 1/2 times 1400 times 0.1 squared, and if I put that in the calculator, I get 7 joules of spring potential energy to start with. That 7 joules of spring potential energy then is going to be converted into gravitational potential energy on this side. Okay, so that will also then that's equal to m, which is 0.2 kilograms times 9.8 meters per second squared times the height 2. All right, so we can go ahead then and figure it out, and we find out that the height 2 is equal to 3.57 meters if we solve for h2. Okay, so that's not quite at the answer yet, but we're getting there. Now what we need to do is we need to figure out the distance r along the ramp. So what we can do is just think about a triangle here. Okay, the height that it went up to was 3.57 meters. The angle is 60 degrees. We want to find this distance r. So we can just use trigonometry. Okay, so remember that sine of 60 degrees is equal to opposite over hypotenuse, which would be 3.57 divided by r. R then, if we solve for that, is equal to 4.12 meters. That's the distance that it achieves along the ramp. So it gets to be, this distance here is 4.12 meters. The next question is, well, what happens if there is friction? Well, it requires a little bit more work, and we need to go ahead and draw a force diagram real quick. So I'll do that here. We see that it's 0.2 times 9.8, and we get 1.96 meters for the weight of the block. Break that up into components. We know that's a 60-degree angle. We can find the normal force if we find this downward component of the weight vector. So that is 1.96 times cosine 60, which is equal to 0.98 newtons. So that in magnitude. And so the normal force then would be equal to the same magnitude of 0.98 newtons. Why do we need the normal force? Because of the fun formula. Frictional force is equal to the coefficient of friction times the normal force. That's equal to 0.4 times our 0.98, and that gives us 0.392 newtons of frictional force. Okay, so we have 0.392 newtons of frictional force. Now the work done by friction, that's going to be equal to this force of friction here times whatever that distance up the ramp is, but we don't know what that distance is, do we? Okay, and they're opposite directions, So the the angle would be 180 degrees between them. Cosine of 180 is -1. So we end up getting 0.392 newtons times whatever that distance r is. And the work done by friction would be negative because the frictional force is pointing opposite of the way it's going to be moved. But this is an unknown. We have an unknown there. That's okay. We can work that out though. All right. So let's use the law of conservation of energy. We have the potential energy of the spring at position 1 plus the potential energy of gravity at position 1 plus the kinetic energy at position 1. Both of these are 0 plus the work done by friction. Now that's the new item right here. Okay, that's equal to the potential energy of the spring at position 2, way up near the top, plus the potential energy of gravity at position 2, plus the kinetic energy at position 2, and remember it's stopped by that time. So that's 0. Potential energy of the spring here is 0. So what we end up with is we end up with the potential energy of the spring, which we remember was 7 joules from before, plus the work done by friction, which would be equal to negative 0.392 R, is equal to potential energy due to gravity, which would be mg times h2. Okay, now we have the R and we have H. We better learn to relate. So let's go back to our little distance triangle. Here's R, here's H2, here's our 60-degree angle. Let me move that up a little bit. R, H2, 60-degree angle. Sine 60 is equal to H2 over R. Therefore, H2 is equal to R sine 60. That's supposed to be an H. H2 equals R sine 60. So we can go ahead then and substitute that in for H2. And so we get 7, let me just simplify this a little bit, minus 0.392 R is equal to, and what's mg? Mg is 1.96. I'll just replace it. Put 1.96 there. And instead of putting H2, I'll put R sine 60. We're almost done, folks. Now we can go ahead and clean this up. 1.96 times R sine 60 is equal to 1.697 R. And on this side it's 7 minus 0.392 R. Cleaning it up a little bit more, we have this is equal to 7 equals 2.09 R, and then R is equal to 3.35 meters, and that's the distance upward along the ramp that block achieves after you release it from that compressed spring. Thank you very much, guys.